So if you don't know the question I'm talking about, it has a person in a building, and the building has a ceiling that is 10 meters above the ground. And they are going to throw a ball from the ground where the ball is in their hand and leaves their hand 1.5 meters above the ground. And then they ask, how fast does the ball have to be thrown so that it just makes it to the ceiling? This is a classic use of conservation of energy. In fact, the thing about this problem isn't the conservation of energy one. What's interesting about this question is what it does after this, because it then asks, how fast is the ball going when it returns to the ground? So the person does not catch the ball returns all the way to the ground. What generally makes a problem a good candidate for conservation of energy is if an object is experiencing a change in height, or the problem is about velocity, or the problem is about the compression of a spring. These are good candidates for conservation of energy. But they're not going to ask it like this. You will have to know when knowing the velocity makes more sense than knowing acceleration. That's what really it's going to come down to. In this problem, though, they're pretty clear. They're pretty blatant. They're asking you how fast the ball has to be thrown so that it makes it to the height above the ground. Now, the reason I wanted to talk about this question is not because of the conservation of energy element. Although I do agree this is a decent conservation of energy question. I think it's a place to start. I think students don't think deeply enough about this question. So first thing I want to recognize is that any conservation of energy question is going to have clear states of the problem, where we're not really interested in what's happening in the middle. We're interested in what happens at specific points. We're interested when the ball leaves the hand. We're interested when the ball touches the ceiling. And we're interested when the ball hits the ground. Those are the three states of the problem that are being brought up. And in those three states, you can compare any two of them that you like. That's what conservation of energy is about. It says that the energy in a system remains constant unless acted on by some external force. So that means whatever the energy is in the system here, it should be the same here as it is here, as long as there's nothing that adds energy to the system or takes energy away. I keep saying that, but people tend to not recognize what I mean by that. And I can only say it so many different ways. So be clear, we're hoping the energy is the same. We're hoping it is. Because if the energy is the same, then the energy at state 1 will be equal to the energy at state 2, and perhaps equal to the energy at state 3. One of the problems we have is ambiguity about gravitational potential energy. And if you don't know what the word ambiguity means, look it up. Get a Webster's. We have three forms of energy that we've discussed in this class. These are the three forms of energy. If you want to make this kind of middle schoolish, we can say that at each location, you should consider which of these forms of energy the object is likely to have. And you can do that at each location. Now, I really don't want to write out these three letters every single time. I do this when I'm teaching like honors physics and stuff like that. I'm hoping that you guys understand there's only a list of 3 items. You should be okay and kind of, recognizing. Now, when you go to evaluate this, I don't know why I put a little K there. I meant to put a little G there. Elastic potential energy. Is the object pressed up against a spring when the guy's throwing it? Unlikely. Is the object moving when the guy's throwing it? Yeah, he's throwing it. That's kind of the whole thing. But here's the ambiguous one. Does the object have gravitational potential energy? I don't know. There's ambiguity here. It depends. The answer to that question depends. We talk about gravitational potential energy as it relates to the object's change in height. From comparing state 1 to state 2, the object's at its lowest point. I could say it has no gravitational potential energy. But when comparing state 1 to state 3, it does have potential energy. Well, which answer is right? Neither. You just have to ensure that when you're comparing two states, you use the same reference point between those two states. You don't even have to have the same reference point throughout the whole problem. You can change it as much as you want. But you have to understand that when you compare two states, during that comparison, you'd use the same reference level. To make this easy for all of us, or at least to make it consistent for this question, so I don't have to keep changing, I'm going to make the ground the reference level for the whole problem. That way I can compare all three states all at once. I'm saying the ground is 0. That means at state 1, I have gravitational potential energy, mgh. And at state 1, I have kinetic energy, 1/2 mv squared. This is the energy at state 1. At state 2, we are told we are throwing the ball in such a way that it just reaches the ceiling. Does the ball have elastic potential energy at the top? No, I don't think so. Is the ball above the reference level? Yeah. So mgh, it is 10 meters above the reference level. Is the ball moving? Not as many people participating with that question. That's an important question. If you don't know how to answer it, then you better make sure whatever I say next is something you write down. At its maximum height, it shouldn't be moving. Will it have kinetic energy if it's not moving? No. This is it. That's the energy between those two states. They never give me the mass of the ball, and I don't need it. Every term has an m in it, so I can cancel out the m. Now, before you run off and start using your calculator, the thing to remember here is we don't actually know if these are equal. Energy at one state is only equal to the energy at the other state if nothing adds or takes away energy in between. You have to assess that. Don't assume. Assess. Was work done on the system by an external net force between the two states? So there's not many things that could do that. I didn't see anybody push the ball up on its way up, besides the guy. I didn't see, we're not usually talking about air resistance, but you need to just don't be complacent. Make sure nothing adds or takes away energy between any two states. They'll tell you if something's going to do that. They'll indicate it's got to slide across the pad where there's friction or there's air resistance or something like that. They will make it clear. Just make sure you don't just blindly set things equal to each other. Now, I'm assuming you guys ran off and started pushing buttons because I can hear the buttons, but I don't care about the buttons. I care about the fact that there's a third state, and if I've chosen the same reference level for all of them, then the energy should be equal at all three states. You can solve the problem in one step. Because when it reaches the ground, does it have any gravitational potential energy? No, it's on the ground or very close to it. Is it pushing against any springs? No. Is it moving? Yeah. How fast is it going when it reaches the ground? It's moving. So this is the V on the ground. This is the V in his hand. They are not the same value. I bet it's traveling faster when it reaches the ground than when it left his hand. Now, does the ball bounce? This is not in the problem, but have you ever thrown a ball that when it hits the ground doesn't bounce? It's hard to find a ball that doesn't bounce. I mean, I know I keep mine all deflated so that they don't bounce, but Most balls, when they reach something, they bounce, which means there's a time when the ball is in contact with the ground where there's elastic potential energy being stored. When the ball is squished down against the ground, it would have elastic potential energy. When all of this energy has been converted to elastic potential energy, we could talk about how much the ball squished as it hit the ground. However, interesting thing, will the ball bounce all the way back up to the ceiling? Probably not. So I don't know that this would be all equal on both sides. There might be some energy that is taken away while the ball is being squished. Like, I bet the ball makes noise. I bet you can hear it. I bet the ball gets hotter. I bet some of the ball changes because of this impact. All of those things would take energy away from the system. So I don't know that these would be equal. I don't know that it would store 100% of that energy when it reached the ground, stop while it was in contact with the ground and bounce back up, which is why the ball probably doesn't make it back to the same height. It probably doesn't go as high now. In fact, you could probably measure how much energy was taken away by comparing these two heights. That's the kind of question I want you to be able to solve, sure. That was the homework question. I think it's a pretty good starting point. Can you follow up? I can increase the level of difficulty or stay about the same. I'm only going to do 3 examples. So we were generally asked to find acceleration, tension in a string. Ooh, that's ugly. Something like that. But at one point, we had a problem like this where the box was some height above the ground, and we had to figure out how fast the box was going when it strikes the ground. Atwood machine questions like this, we would have solved for the acceleration using net force, and then probably set up a motion problem. But you don't have to. Is it clear in the context of this question that one of the objects experiences a clear change in height? Change in height is a good indicator that conservation of energy will be the simplest way to solve your problem. So if something changes height, you should consider, again, tends to be these things when we deal with conservation of energy. Changes in height, changes in velocity, changes in the displacement of a spring. So if you see some of those, strongly consider conservation of energy. I see another state of this question. The state where the box on the table has been moved to the right while the box that is hanging has fallen to the ground. This state, the box now has velocity as the box that was above the ground has fallen to the ground. Let's say 3 kilograms, 2 kilograms, and state 1 and state 2. Let's say that this is a 0.75 meters, and let's say that this is 1.2 meters. The Atwood machine is an excellent example of another conservation of energy problem. This is a modified Atwood machine, so only one of the objects changes height. On a true Atwood machine where you have a box hung on both sides, then one object is moving upwards, one other object is moving downwards. So understand that that Atwood machine would be a little more complicated. Starting with this one because it's relatively simple. Don't get me started on the one that has like an incline and this, that's going to be fun times. The real question comes down to, can you figure out how the energy plays a factor in this problem? That's what this one's about. Consider the box on the table. Does the box on the table have gravitational potential energy? It's an ambiguous question, isn't it? Does it ever change its height? No. So you don't have to worry about its gravitational potential energy. It never changes height. Because of that, does its gravitational potential energy cause the system to move? No, it never loses any. So you don't have to worry about it. If you're concerned about it, again, the safest route is to always make the reference level the same for all of your objects. That is the safest route. So we could say, sure, it has a gravitational potential energy, 3 times 10 times 1.2. That's how much gravitational potential energy it has at state 1. How much gravitational potential energy will it have at state 2? Well, 3 times 10 times 1.2. You notice it's just going to cancel out, right? So yeah, I can include it. I don't need to. I know the box that's hanging has gravitational potential energy, 2 times 10 times 0.75. That one it does. It does have gravitational potential energy. It is above the reference level. There's no springs here. I'm not going to worry about that. I release them both from rest. There's no kinetic energy when I start. Is that okay so far? Do we both realize that in state 2, both boxes are moving? Right? Both of them moving. If it's the same string, they're both moving the same speed. Just like in first semester where, I'm sorry, last time I talked about this where they both have the same acceleration. But box 2 is going to reach the ground, so it loses its gravitational potential energy. So when I look at this problem, I hope you see it too. This canceled out. The real energy of the system started in a potential energy of just the one box, the hanging box. And that gave us kinetic energy in both boxes. So the energy that the one box had as it fell becomes kinetic energy in both boxes as it reaches the ground. Now the ground is going to absorb the kinetic energy of the 2 kilogram box, but the 3 kilogram box can just keep on going. Again, I don't want to work out the answers. I don't care about the answers. But do you see how this problem works out? Any questions about it? All right. You got to make a problem out of it. But I see a problem here. Like, if I want to make it over here to this location, what is the minimum distance I have to pull the car back against the spring in order for it to just make it over the top of the hill? You guys understand what I'm asking? Because the question I'm asking isn't about this location. The question I'm asking is about this location. The minimum distance I pull the spring back is the distance necessary to give the car enough energy to just make it to the top of the first hill. If I want to solve this problem, I'd have to compare the amount of energy the car will have when it's compressing the spring to the amount of energy it needs to have to make it to the top of the first hill. Try it. This one I'm going to see if you guys do it. There's nothing more for me to do. I mean, you'll need to know things like 1/2 kx squared and mgh and 1/2 mv squared. This is not the actual question I wish to ask. This is just a start. If you're super, super smart and you're getting all this, you could figure out maybe how fast it's going here. That's a different question entirely. But for you guys who are just starting out, get that distance. How far back do you have to pull the car so that when you release it, makes it to the top of the first hill? And you guys have a little bit of practice doing this without a net. So state 1 will have no kinetic energy. It's the spring that causes it to move. So we'll just have 1/2 kx squared. And then to just make it to the top, all the energy is going to be in the form of potential, 0.25 times 10 times 1.2. Now you'll notice when we have elastic potential energy that the mass doesn't cancel out any longer, because the amount of energy stored in the spring doesn't have anything to do with the mass of the car. So working out how fast it's going over here, we actually didn't have to use the spring at all, did we? I also want to point that out. It's not necessary to know how far the spring was pulled back to realize that this also has to equal 0.25 times 10 times 0.8, the potential energy it has there, but it also is going to have some residual kinetic energy. So you can solve for how fast it's going here on this ledge without actually having solved for how fast it was going. How far you had to pull the spring back. Now, you'll notice once you've done a couple of conservation of energy problems, they are all the same. We are setting one state equal to another state. That's not what these problems are going to be like. Conservation of energy is a means to an end. So I want you to consider that I drew this carefully so that I could do this. The top of the ramp has a radius of curvature of 0.3 meters. We just found out the minimum distance we can pull the spring back for the car to make it to the top. But there's clearly the other side of that. If I pull back too far, when the car makes it to the top, it won't nice and cleanly go over the top. It will lose contact and become a projectile because it won't remain in centripetal motion. So there is a maximum distance that if I pull the car back too far against the spring, I will shoot the car over the top instead of having it come down nicely on the ramp. So what is that maximum distance that I can pull back the spring? Now, before you guys launch into that, let me just be very clear. That is how we're going to see conservation of energy. Not as a standalone problem asking about how fast something is going, but giving you a problem where knowing the velocity is necessary to solve another portion of the problem. I have a constraint. When the car is up here, there are two forces acting on it. I know that for the car to stay in circular motion, the net force has to be equal to MAC. This is the kind of stuff they're going to do with conservation of energy. They're going to put it with another question, for sure. There's never a pure conservation of energy problem. It's always going to mix this stuff up. In this problem, we make downwards the positive direction. Let me draw that back in there. Because we want to say that mg minus the normal force equals mv squared over r. That's the kind of thing we want to do. And we know the max speed is when the normal force approaches zero. Well, we might not all know that, but we're supposed to, because we've done this question before. This tells us what V max for the car is. So state one still is going to be elastic potential energy. But state two now has gravitational potential energy and a maximum allowable kinetic energy. Kinetic energy is how fast the car is going. Since there's a max velocity, there's a max kinetic energy. This is the kind of thing you're going to be asked to do. To set up a problem where you'll have a constraint. In this case, the constraint is keeping the car on the track. You'll use that constraint to figure out what the max velocity is. mg equals mv squared over r. This is max. So I set the normal force equal to 0. Now, we've done this problem before. So I know that, that was a while ago, but that doesn't change the fact that we've done this. I shouldn't have to do it again. Cancel the m's out, solve that for v max. So v max, square root of gr. What does that mean now? All right. The height is still, whatever it was, 1.2. But now I've got this K max, which is 1/2 mv max squared. That has to equal 1/2 kx squared. I don't want to do the arithmetic. You can plug numbers in and get answers. I want to show you the types of problems that are here. We've done this problem before. We've done this problem now. We're just putting them together. Let's take a look at another one. And by the way, with that car on the spring, what you're looking at is just a toy. If you're making toys, you want to make sure that there's a spring in there where you can pull it back far enough to get over the hill, but maybe not make the spring so long where you pull it back far enough to shoot the car over the top of the hill and hit your brother in the face. Right? So there are safety concerns. They make those Hot Wheel kind of toys all the time. They design them to work within certain constraints. So, pendulum problem. I don't know if it occurs to you, but if you pull back a pendulum, when it swings downwards, you realize that it's got potential energy here, which means that when it makes it down to the bottom, it's going to convert that potential energy into kinetic energy. Does that make sense? Does it also make sense that if this is a pendulum, this would be the lowest position it could attain? All right. Since everybody's nodding in agreement and is all happy, I'd like you to tell me if you can figure out how high the object is in terms of the angle you pull it back and the length of the string. Because I don't know anything about it. I've got pendulums. They don't tell me how high they are, but I can see the angle real easy. I measure the length of the string real easy. I bet the more I pull it back, the faster it'll be going at the bottom. Seems to me there's got to be a relationship here that would show me that it'll be going faster and faster at the bottom based on how far back I pull it. Can you figure this out? My experience has been mixed with students here. And although I'd love to give you all the time in the world, you understand I'm not going to, right? We just don't have that kind of time. But I'm going to help some of you so that maybe some of you will see something. Can everybody agree that that's got to be the height of the object? That has to be the height? Now I'm saying this because you know that if you pull it back 90 degrees, the height should be the length of the string. Right? If I pull it all the way back to here, shouldn't the height be the whole length of the string now? So whatever expression we get, when theta is 90, the height should be L, the length of the string. The question is, can you come up with what this expression should be? Can you get H in terms of L and theta? I don't know if you can or not. I'll give you a second to think about it. I'll give 30 seconds for you to think about it. Some of you should be able to do this. Some of you did this last year. Well, you guys are thinking about it. I'm just going to identify some stuff here. Okay, see that triangle? If this were the hypotenuse, then this has to be the adjacent side. And this is the clincher. That has to be true. Does everybody see why that has to be true? It's the same length string. Now, this is easy. This is L cosine theta, which means this can be written as H plus L cosine theta equals L. So generally you factor the L out when you write this. When cosine is, when you take the cosine of 90 degrees, you get 1. And 1, I'm sorry, you get 0. And 1 minus 0 is 1. Works perfect. Pull it out 90 degrees. I get that the height is L. When you have 0 degrees, cosine of 0 is 1. 1 minus 1 is 0. So if I don't pull it back at all, there's no height. Makes sense. Now look, I don't care if you can work this out or not. You can memorize this. Memorize it. You don't have time in a multiple choice test to have to prove this every time. They put this on multiple choice all the time. For all pendulums, any circular object, a circular hill, this is how you can find the height really fast. So please memorize this. I gave you a homework question where it's this problem just inverted. It's a sled going over the top of a round hill. It is a classic physics question. It's super hard. So if you don't get it, fine. It's all right. It's a tough one. But for those of you who are smarties, and I got some in there, you should do it. You should be able to get close. It comes out to a specific answer, so you'll know you get the angle right. And it's an odd number one. You can check it in the book. On the other hand, do you guys see this problem now? Do you see that we've got MGH here, which could be MGL 1 minus cosine theta? Do you see that? See that over here then we could have 1/2 mv squared? Are we together on this? Well, I can show velocity in terms of the angle, can't I? In fact, if L is bigger velocities. So when you go to the swing sets at the playgrounds, you want the longer ropes. You want the swing that's closer to the ground. You go faster. Everybody knows that. Well, maybe you don't know that. I know that. And of course, the further back you pull somebody, the faster they're going when they make it to the bottom. Of course, that's this portion. But here's the part you're not thinking about. Here's the part that is going to stress you out. Because if this hasn't stressed you out yet, then the real question should be, what's the tension in the string? Right? Because that's the problem. That's where we're going to see something. That down there, there's tension upwards, which has to be greater than weight downwards because it's traveling in a circular path at the bottom, which means the net force has to be equal to MAC. Boy, they love the circular problems with motion, with conservation of energy. They love them. Do you see the problem I see here? I do. I see a problem here. I see a great problem. Because this is going to be tension minus mg equals mv squared over L, right? Radius is L. Do you see it? You got to see this stuff. And I see a way of expressing the velocity in terms of the angle that you pull it back. Oh, come on, these problems are clearly connected. Yeah, this is the kind of stuff. So when we did all those circular motion problems, they were about preparing you for this. This is what we're going to do. And you know, we're going to have to address right? How high do I have to release the marble so it still makes it all the way through the loop? It's not just anywhere now. The condition for the height here is about how fast it has to be going here. But how fast it has to be going here is a force problem with centripetal acceleration. This problem is done, it's on the exam every other year. Once you've done it a couple times, it's not terrible. You'll have to understand that there is a minimum height necessary. And it's not arbitrary. Every roller coaster is based on it. Now, the bell rings in like a minute, so we don't get this problem today. But that shouldn't prevent you from looking up this problem that we did earlier in the year. And realizing that all I got to do now is add mgh and 1/2 mv squared to get the next part of this problem. We did this problem yesterday, but we didn't talk about the centripetal force portion of this. We just talked about roller coasters with loops in them. But you can't just place it anywhere. It's not any speed you have to be going here. You have to be going faster than a certain speed to make this work. So what I'm trying to show you is that these problems aren't going to be about energy by themselves.